Today we're going to go down the rabbit hole, explore the JVM internally a little bit, and hopefully give you a way to learn more about your applications and be better developers. So the preliminaries here, Charles Nutter, Charlie to my friends. I've been at Red Hat for about 5 years now in our research and prototyping group, which basically means we just play around with weird stuff and see if anything happens. I have been working on JRuby for the past 10 years, full-time. First at Sun Microsystems, then at a company called Engine Yard, and then later on at Red Hat for the past 5 years. And my work on JRuby is largely in compiler work, optimization, digging into deep, low-level details of the JVM, trying to get Ruby to run as fast as possible. And so that has required me to dig into a lot of JVM internals and learn more about the JVM than I ever wanted to know, which I will now give to all of you here. And I'm hideous on pretty much all the services, so you should be able to find me easily enough. So the JVM is a wonderful world that we live on here. We throw code onto it, it optimizes, magic happens, and our applications run well. But sometimes it feels a little arcane. We've got our weirdly speaking, unusual JVM engineer who seems smart, but doesn't actually seem to say anything we understand. And here we are, down at the bottom, trying to understand what's happening in our code. What is happening with this JVM? And really, the thing is, we've got these applications, we've got our world of Java and our libraries and Maven and Gradle and Java EE and everything else, but all the interesting secrets of the JVM are down here, inside this little door, and we can't quite fit through. We don't know how to see what's happening inside the JVM Wonderland. So today, we are going to drink the unusual JVM fluid that we have found and shrink down into the JVM and see if we can explore a bit more what's happening at the JVM level and understand why our application works, and more importantly, why sometimes it doesn't work the way we want it to. All right, so here we go. What are we going to cover today? Well, we're going to look at some interesting typical Java features that you've all likely used. We're going to see first how they compile down to bytecodes and how to read those bytecodes and understand the code that we get from Java-C. We will see what the JVM does with them, how it decides to compile them, how it decides to optimize them. And then, yes, we will actually look at the native assembly code that the JVM produces, the code that actually runs on the CPU, ideally, once it optimizes code. So first of all, taking a small step back, why would we want to do this? Well, it matters who you are. Obviously, most of us here are Java developers. Some of us may be performance engineers in charge of optimizing applications, finding bottlenecks. Many of us have to do some debugging at some point, find why an application isn't working right, why something doesn't do what it's supposed to do. But really, in the development world, we're all of these at some point in our lives. We write the code, we debug the code, and we optimize the code. And we need to understand all of the processes that happen at the JVM level. The truth is that these details matter. All of these cool features that we have on the JVM, like lambdas and so on, they all have a hidden cost. And if we understand that cost, we can make better decisions about which features to use and how to use them. And how you write code is going to impact the performance of your application. The more cool new features you use, the more those features are going to impact the way your application runs. And so today we'll try to understand a little bit what the JVM can and can't do for you and how to do a better job. So the first concept here, and one of the big reasons why we need to learn this stuff and why this is important to know, is the idea of the sufficiently smart compiler. So the idea here is that you have if you have a low-level language, like a C or assembly or so on, and then you have a high-level language written on top of it. All you need to make that high-level language run as well as the low-level language, to make Java run as fast as C, is a good enough compiler. It just has to be smart enough. And if we apply this to the JVM, the idea, the standard Java world, is that if you wait long enough, your application will just magically optimize, and you don't need to worry about the code you write. The JVM will be smart enough, and your application will perform. And now the problem here is long enough has many definitions. Of course, this can mean waiting for warm-up in production. Sometimes we have to run our application a few times to make sure the JVM's optimized it. Sometimes this may mean we wait for the next JVM version when the JVM engineers do their optimizations. Sometimes this may never happen. Long enough could be more than our lifetimes of waiting for the Java VM to figure out what we actually need to optimize. And the truth here is that a good programmer can always defeat a good compiler. We can always find a way to trick the compiler and make it sure it can't optimize code. So it's very important when you write code on an optimizing VM or on any compiler to know your runtime and to understand how it makes these decisions to optimize code. Okay? So let's continue on. Short primer here. So a little vocabulary. Of course, in our world, source code is all just the Java text that we write. In many languages, that's the last step of writing your code. You run the source directly, as with Python or Ruby, for example. But in our case, we have to do a compile step. We compile it down to bytecode. And this is the binary form that works across all JVMs, a platform-independent representation of our Java code. And then the JVM runs that and does something to it, and eventually we should get down to native code running on the processor. Everything has to run on the CPU at some point, and ideally the JVM will turn our bytecode into native code. And it does this through one of two processes. The first process is JIT, just-in-time compilation, which we should be familiar with as Java developers. The idea here is that we throw our code into the JVM, it decides when it's a good time to turn it into native code, and then optimizes it at runtime. So we don't have any native code sitting on the file system. We usually just have our bytecode, and the JVM makes the native code as needed. Now, more and more on the Java world, we hear about AOT, ahead-of-time compilation. This is compilation that we do before we execute the application. We compile it down to native code, and then when we run it, that native code is what's executed on the processor. There's various different versions of this. For example, the CLR, Microsoft CLR, is essentially an AOT runtime. No code runs on the CLR runtime unless it's already compiled to native code, but it does this lazily. Like the first time you run the application, it turns it into native code, and then it continues on from there. But in the JVM world, we're mostly going to be interested in JIT. And the general process of JIT in the JVM, so we have our Java source into JVM bytecode. That's an easy enough step. And most Java developers just kind of stop at that point. I've got bytecode, I have a JVM, it works. But inside the JVM, our bytecode will be run inside an interpreter of some kind. Pretty much every JVM has an interpreter. Some only have interpreters. And while it runs in the interpreter, it will gather information about how that code runs. It will see if we're calling the same method every time. It will check which branches are being followed and which ones aren't. And then it makes decisions about how the code should optimize, what it looks like for the best possible optimized version, and it passes that on to the JIT compiler. The JIT compiler then takes that information, takes the code, and produces native code that ideally runs as fast as we're hoping it to run. And now in most JVMs, this process will cycle. The native code may turn out to be wrong. We made a decision early on. We're not actually calling the same method later on. We go back into the interpreter, run it a little bit more, gather some more information, and the cycle repeats. Ideally, a typical JVM application will settle all into native code. We won't be going back into the interpreter very often, and then we get our straight line performance. We're warmed up, and we're ready to go. And now what's interesting is what that performance looks like once we're warmed up, and how do we get there? So first step is that we want our application to get down to native code. Even the best interpreters can't compete with a good JIT, so we want to know that our application is compiling down to native code. So a little more vocabulary here. Optimization, this is a definition I like to use. Doing the least amount of work to accomplish some goal. The visible result of your application, getting there as fast as possible without wasting a lot of time, without accessing more memory than necessary, without executing more instructions than are necessary. And probably the biggest way that we get here on an optimizing runtime like the JVM is through inlining. This is where we take two methods and combine them into one. If it turns out we're always calling the same method, well, let's not actually do a call. Let's just take that method's code, stick it in the original place, and run it as if it were all together. So a little bit more graphically, inlining here. So we load our target object and the arguments we're going to pass into it. We do a test to see. Are we calling the same method again, the same class? Nothing else in the system has changed from the last time. Well, in that case, let's just run that method's code directly. Don't make the call. Don't call through an interface or through a virtual method on an object. Let's just put that code there and call it directly. If it turns out it's a different type, well, then we need to go look up the method in some method table, do a branch out to that call, and then run it as a separate piece of logic. So our goal number 2 is that we actually optimize the native code and get a good result out of it. And that, of course, means we inline it. It means that we look at those branches and turn the code into what's fastest and least amount of work to get our application running and to do our job. Okay, so the tools that we're going to look at today, Java-C won't be mentioned here, but obviously that's what we use to get our bytecode. The Java-P tool to dump out class data, so we can see the bytecode that's used. And then a number of flags for monitoring the compilation of our code to make sure it's being turned native, the inlining of code to make sure that the JVM is inlining what it should, and then, yes, actually looking at the assembly code. So down we go. So we'll start with something very simple. Perhaps the largest hello world in the programming language community. Everybody's written this code at some point. So let's take a look at level 1 first of all, just looking at the bytecode. And this is today we're going to use the Java-P tool. Many IDEs also have plugins that let you just bring up a class file and browse the bytecode in it. But it's very simple to just go to the command line and run Java-P. If we just run it directly, what we get is basically a pseudo-Java structure of the file. And this is actually kind of a nice way if you're at the command line, can't remember what methods are in a class, you can run Java-P, give it the class name, and it will dump out this general structure. Now it gets more interesting if we pass the -c flag. -c will then also dump out the bytecode for each method. And now we have our first view into the bytecodes that are created by the Java-C compiler. So we'll walk through these 4 sets of bytecodes directly. We have our example here. So first of all, we get a static field, system.out, which is a print stream in this case. We load a constant. LDC is the load constant instruction. So we load a constant string, hello world, onto the JVM stack. We do a virtual invocation, which is a method call against a class, rather than an interface, for example. There's also invoke interface, invoke static, and so on. And then this is a void method, so we do just a simple return. There's also iReturn, lreturn, and so on for different types of JVM objects, numeric values or references. And so this is fairly simple. Now we can kind of read through the code. Once you understand the basic set of bytecodes, which there's around 200 or so bytecodes that are available, you can understand how Java-C is producing this bytecode. But we'll move on. We'll go down to the next level here and actually look at what the JIT compiler is doing. So there's 2 flags we'll look at here, print compilation to show methods as they compile, and print inlining that shows the inlining process. So in the Hotspot JIT, as I mentioned, code is interpreted first. And so initially we won't see any compiles happen. The application needs to run for a little while, and then at some point, perhaps after a certain number of calls, perhaps after a loop runs for a certain amount of time, the JIT will fire and create native code for us to execute on the processor. And now in the older Hotspot, there were 2 versions of this. We had the client compiler, which did a very short examination of the code and produced pretty good native code. Not very optimized, but we got there quickly. The server version would run it longer, gather more information, and then it would produce much more optimized code, better code for our applications. These days we have what's called a tiered compiler. So initially it starts out in the client mode, gathers more information, and then we'll also go to the server mode. So ideally we get fast startup and we get fast performance once it's warmed up completely. And for this case we'll disable tiered compilation so that we don't have that as noising up the logs. We won't have as much compile noise when we do the monitoring. So we'll do our hello world again, but we'll loop a number of times. Here we're doing 100,000 to make sure the JVM sees that this is hot code and it needs to JIT it. By default, the server compiler would compile at 10,000 calls, and then there's certain ways that it examines loops to see if they need to compile as well. Here's our command line. So xbatch here will turn off parallel compilation. So normally the JVM will compile your code in the background, and that can kind of splice results together in the logs. If we turn on batch compiling, we don't get that interspersing of results. I mentioned we'll turn off tiered compilation, and then we'll pass the print compilation log, which is just a standard flag on OpenJDK or Oracle JDK. And we get a result that looks like this. We have our list of methods, and we have some arcane numbers here. On the far left, this is the number of milliseconds since the JVM started, so we have a timestamp of when the compile happened. We have a compile count, an index, so the first compile, second compile, third compile, and so on, which can be referenced later as we re-optimize code. There's this bang or exclamation point. That indicates that this method has try-catch logic in it. And so the JVM has to make different decisions about how it optimizes. Down here, this %sign means that this method never actually exited before it compiled. The JVM decided while that method was running that it was hot, it probably should be optimized, so it branched out to native code while it was executing. It's called on-stack replacement. And then, of course, over here we have our method name, class name, and the size in byte codes of the method. And so now we can see from this output that the two methods we're interested here, hello world hello, that prints out hello world, it did compile, it was about 9 bytes of byte code, and our loop in the main class actually compiled. It ran long enough, it was hot enough, the JVM replaced it while it was executing. So let's take another look. We'll actually look at inlining and see if the JVM is inlining code the way we want it to. Now there's two new flags here. We're talking about a diagnostic option, so this is not normally enabled in the JVM. We need to tell the JVM to turn on inline, print inline logging. So unlock diagnostic VM options, and then print inlining. And now notice we still have print compilation here, so we have our compile logs mixed in with the information about inlining code. And now we get a little bit more output here. We still have our two methods, main compiled and hello compiled, as we expect. But we can see all along the way here there's a number of methods that were inlined. Hotspot decided that these were hot methods. They needed to be inlined so that we could reduce the cost of making those calls. Further up in the execution, early on, character buffer handling, loading code from the file system, processing strings. That was hot very quickly in the JVM execution. Later on, while our application ran, the print line function was seen to be hot enough that we wanted to JIT that. And so that actually got inline too. And now what's interesting here is you can also start to see why certain methods didn't inline. Up at the top, the index of supplementary was too big. The JVM has limits on how much it will decide to inline code. And some of those limits are rather small. This is only 71 bytes of byte code, but Hotspot decided it was too much code to actually do the inlining. Down at the bottom, hello had already been compiled and inlined with a whole bunch of other code. It didn't want to continue inlining that. It decided it had already done enough work on hello and didn't inline it into the main method here. So this is interesting if you've got a hot algorithm, some numeric algorithm that you're working on, or some complex code, you can see which pieces are inlining and which pieces are not, and maybe make some restructuring, make some changes to your code to get it to optimize better. All right, so we know it's compiling, we know it's inlining. Let's see what we actually get from the native code. So we're going to use the print assembly flag here. And this is not normally shipped with OpenJDK, Oracle JDK. If you want to grab a binary plugin, you just drop it into your JVM. Google for Hotspot print assembly. There's several builds out there for different platforms. Just a dynamic library you can throw into your JVM, and then this flag will be available. So here we have our print assembly flag, and down we go into assembly code. How many people have done assembly at some point? All right, there's a few folks. Cool. So some of you will recognize this. There's a lot of noise here, obviously. And in this case, thousands and thousands of lines more assembly code as a result of this. Too much for us to look at right now. In this case, for this example, the server compiler produces about 2,700 bytes of assembly. Lots of code, too much to read through. Even the less optimizing client compiler still produced almost 600 bytes of assembly. Now most of this output is due to all the inlining that happens. We're inlining print line, which inlines a bunch of I/O operations, which inlines a bunch of character manipulation. So all of that noises up our output, and it's hard to see an example here. So we'll go with a simpler example. We're just going to loop calling this method tiny. Tiny is just going to add 1 + 1 and return that value. So now immediately, if we look at the bytecode, you'll see Java C has already been a little smarter here. It knows that 1 + 1 is always going to be 2, and so it just inserts the constant value, 2. So we don't actually load 1, and add the 2 values. There's no need to do that. We just load the constant 2. We can see that we've got our code compiling here, and the tiny method works out to 2 bytes of bytecode. That's the load of the constant value 2 and the return. We have our main method, which is larger because of the loop, and we see that the tiny method also inlined because it was being called a lot. Now we go into assembly code. Here is our tiny method, and there's a little bit of noise here I'll talk about in a bit, but the interesting instructions here are these two. We move our constant value 2 into the EAX register, and we return it. And return uses the EAX register as the result of this function. So we've got our code. We'll talk about the other JVM logic here in a minute. So what does it look like for the inlined version, main plus tiny, when we've got them both inlined together and optimized? Well, there's much more code here and much more noise. And so we're going to try to parse this out. There's a lot of helpful comments in here that say where this code is in the JVM, or in the Java code. There's a lot of memory addresses, 64-bit memory addresses, and some JVM plumbing and whatnot. So we'll clean this up a little bit. So first of all, we have these instructions at the top, move, push, and sub. Down at the bottom, add and pop. And so this is managing a native stack. Every method that executes on the CPU needs a place to store its arguments and its local variables. And so what we do is we bump a pointer along, grab an area of the native execution stack, put all our local variables there. We work with those while the method runs, and then eventually we pop that stack frame off and return to the original method that called us. And so for our purposes, this is just preamble, postamble code that is in every method that's passed down to the native assembly or native processor, and so we can ignore this for now. Now we have these 2 test instructions that look unusual. These are what's called in the JVM a safe point. At this point, the executing code asks the JVM, do I need to run garbage collection now? Should I deoptimize this code? Is there something else that needs to be done? Basically pinging the JVM every once in a while to see if something should change, if the universe is not what it was before. Now, too many of these in your code can certainly hurt performance. And even more so, sometimes these interfere with profiling. Some of the profilers that we have on the JVM only run at these safe points. And so we can get a skewed view of how our application executes. In-depth discussion of that, there's many other better talks about safe points and how they work, how to optimize around them. And so for our purposes, we will just also remove these from our code. Now we have this unusual instruction that doesn't seem to do anything. We're going to exchange a register with itself. Well, this is actually just a no-op. And it's encoded exactly the same as a no-op in x86 assembly. Depending on which format you use to print out the assembly, it will show up as exchange EAX, or a NOP basically does nothing here except to align the code on a particular boundary, 32-bit, 64-bit. Most processors would like the codes to be on a particular boundary. It helps speed the process of decoding them into microcode and then executing it on the hardware. And so for our example, of course, this is not interesting either. And now some of the remaining noise here is mostly just because this is dealing with a native processor, and we've got all of these long and gnarly hex codes here for memory addresses and for values. And of course, we can read this given enough time, but ideally it's nice if we can see this as decimal to understand it a little bit better. So we'll take these and we'll turn them into sort of logical addresses rather than actual addresses and decode some of these into decimal. And so it gets us down to this code. And now this is certainly much more approachable. This is the sum total of the main method and the tiny method inlined together and optimized, if we remove all the other boilerplate around it. And if we walk through this code, up at the top, we move 0 into ESI. So ESI in this case is our I local variable, our int variable. So we initialize our local variable. We have our logic to do the branching. So first of all, we jump down to a test. We test if this value is still less than 100,000. If not, if it's still below 100,000, we jump back up to line 3 there. Line 3 is our increment of the I variable. And then eventually we exit the main method. And now the question that may come up here is, what happened to this? Where is our logic from the tiny method? Well, now remember, optimization is only doing necessary work. So if we go back to our example, the tiny method returns a constant value that is never consumed. It's never printed out, it's never written into memory. There's no reason to do that logic, and so it basically disappears. And then if we continue on with this process, we've got, oh boy, 15? Okay. So if we continue on with this process, the loop itself actually doesn't do anything, and the JVM may eventually optimize this down to just return. And so now we can see how we can watch over time and see how the JVM optimizes stuff. And it's really not that hard to understand this code once you know what you're looking at. All right, so part 3, Wonderland. We're going to have to move quickly through here. So these are the features we'll cover: Java final fields, synchronization, string switches, and lambdas. So final fields, of course, on the JVM are fields that can't be modified, maybe should be in quotes, because through reflection we can always cheat. But in general, the compiler can take advantage of this. So here we have an example of 2 static final fields. We'll initialize one directly with a constant value. The other one we'll get from a property. And we'll look first at what the Java C compiler produces here. So we have our directly constant value of my string, right? So first of all, here's our code for the system out print line. We've seen that before. We can read past that. We have our my string, which was initialized directly in the code. And Java C actually will stick this code into every usage. Everywhere you use a constant value like this, it puts it directly into the bytecode. And that means if you change the source class, you also need to recompile all of those other classes. It's something to remember. Perhaps you've run into it in the past. If we look at the other one, though, this is lazily initialized. Java C can't see this value, and so it always needs to go get this value. It can't see a value that's created at runtime, and so it has to go and get the value every time. So what about on the JIT side? Well, here's a slightly different example. So we have my string and my property in this code. Here is the assembly code we get out of it. And the JVM is actually smart enough at runtime, once the final has been initialized, even if it comes from some dynamic value, that in both cases, it can actually insert the direct reference to that string. Now, this is a fairly new optimization in the JVM around Java 7 or so. And so this is good. It's actually seeing through our get property and inlining that value directly. Now, if we look at an instance field, it gets a little bit different. So we have our directly initialized final string, and we have one that's, again, from a property. Now, these are instance fields rather than static ones. So Java C is still pretty smart here. It can see that all paths to initialize this object, to create a new object, are going to get the same string, and so it does inline that directly. But the field, the one that's really lazy, it has to go get every time. So similar to the static fields here. Now at the native level, of course, our direct one, we can see that the JVM inlines the reference directly, and it's not actually going and getting the field each time. But the other one, it does have to go into memory each time and go grab that field. So even if a final field is the same each time, Hotspot still might not be able to reference it directly. It might not be able to load that pointer directly into memory. So here, we found something already that Hotspot might be able to do a better job. If we have a hot loop and we're reading a final field over and over again, maybe we don't need to keep reading it every single time. Maybe we can optimize that a little better. So in the future, maybe that will happen. All right, concurrency. So we'll look at synchronization and volatility. So here's our synchronized example. We have basically the same method, but one has synchronized on it. And we'll see how the JVM actually optimizes this. So first of all, we look at the bytecode. Nothing looks different on the call side. So the calls look exactly the same within the main method. And the only difference we see in the bytecode for each of those methods is this flag here is inserted into it. So it knows that whenever this method's going to be called, it has to do the appropriate locking logic. If we look at this at the native level, here is our unsynchronized version. As you'd expect, fairly simple. It moves the system class into a right location and then invokes current time milliseconds and returns. No locking logic, not a lot of extra noise here. Now, what about the locking stuff? Now we get some interesting code. Now we start to understand the overhead of locking. And this starts to look pretty scary if you see this in your assembly and you're trying to understand it. Now again, the interesting bit is still right down here at the bottom. We move the system class into a value, into a register, and then we call current time milliseconds. And the rest of this, what is all this noise up here? So we've got much more code than just our current time millis. Well, so this is logic for the reentrant locks we have on the JVM. So every object has a bit on its header that says if it's been locked, essentially. So each time we need to lock an object, we have to check that bit and see if it's already been locked. If it has, then we can just go right into the code and we know we're safely controlling this object. If not, we need to branch down to the locking code. So here, up at the top, this basically, all this logic does, we load our class, so this is a static method, we load our class object into memory, we pull those header bits out into a register, we check the particular bit we're interested in, which is the locking bit, compare it with a known value, and then if we've already locked it, we can continue on. Unfortunately, if we've not locked it, then we need to branch down to a completely separate bit of code. In this code, we again load the class, we get our bits in place, we OR our bit into that locking location in the header, and then we execute right about here, we execute our lock instruction that will actually write those header bits. Now the object is locked, we own it, and we can continue executing. And then we jump back up to where we were before and continue the code that's supposed to be synchronized. So what about volatility? Well, volatility basically in the JVM forces memory ordering, forces writes to memory, makes sure that everybody sees a consistent view of objects. And the process is very similar to locking. So here's a real-world case. One day I was working on optimizing JRuby, and suddenly for some reason all the benchmarks, every one I ran was 3 to 5 times slower than it was just a week prior. Profiling showed nothing. All the same methods were hot. The compiler logs looked okay. The things that I expected to compile were compiling. So I needed to go deeper. And this was the first real case in JRuby where I had to get down to assembly code to find the problem. And what I saw was this code. So here, our Ruby basic object, this is the top of our object hierarchy in Ruby. This is our Ruby basic object constructor. And what I noticed here is, why would we be doing a lock? This isn't a synchronized constructor. I'm not doing anything like that. I'm not doing any volatile writes inside my constructor. Why am I getting the overhead of this locking instruction? And what I realized very quickly was that I was actually doing a volatile write every time the object was being constructed. For every object in the system, which included all numeric values as well, this maybe was not such a good idea to do. You may have seen this pattern in your code. So in my case, I wanted to avoid the null check every time. So I initialized the variable table early. Well, that was not such a good idea. Doing a volatile write every time slowed down the entire performance of the system and destroyed any gains I would have gotten from avoiding the null check. So achievement unlocked here. I fixed a performance bug in JRuby by looking at assembly code. Okay, moving on quickly. We'll look at string switch, which came along in Java 7. Very exciting feature to have. Lots of folks have wanted this for years. But how does this really work? So initially, we'll talk about basic switches here. There's 2 different types of switch at the JVM bytecode level. We have a table-based one, if we have a narrow range of values, and a lookup-based one, if the values are very different. Now the interesting bit here is that these two have very different execution characteristics. The table switch will go branch directly to that line of code and execute quickly. It doesn't have to do a lot of extra processing. But the lookup switch is log n. It does a binary search. In code, looks like this. We have our 0 case, 1 and 2, all of these nicely in line, one right after the other. This becomes a table switch in the code. It just looks up the value in a table, finds the instruction to branch to, and continues on. Here is a case that turns into a lookup switch. We have values that are very far apart, not logical for us to try and stick these into a single table. And so this becomes a lookup. It sorts these values so we can do a binary search for the right one, and then it will branch to the right offset. So what kind of switch do we use for a string? We can't just use a table because different strings may have the same hash codes. And if we just do a lookup, well, we still may collide with the different strings. And so if we have a switch like this with 5 different string values, the code that actually comes out of this from the JIT compiler looks like this. What we have here, we have the hash code, because this is a standard way of doing hash codes on the JVM. We grab the hash code out of that string, and we have a first switch that goes based on hash code. So this will be a lookup switch. So we figure out which of these hash codes match up, and then we still need to check that we've actually got the right string. So we check if it's the Scala string, Groovy string, and so on. Once we've determined we do have the right string, we set another value. Now this value is used down below in another switch. This is a table switch. So now we know it's the second case, and we can branch to love IU for closure, for example. So surprising amount of code that's actually created. What we've actually got here is JavaC creating a little hash table for us in the bytecode directly. And it's significantly larger than just doing one switch. So size matters for JIT compilation and optimization. So interesting to know, keep in mind this when you use the string switch. The larger it gets, the more code you're creating. All right, and the final case. So we'll look at Lambda Expressions. Very exciting again in Java 8. I was looking forward to this after being a Ruby developer for a long time. Now the key goals here would they be lighter weight. We don't have classes for extra class files on the file system. And ideally, the JVM would optimize them well. So here's our little harness that we're going to use. We've got our 5 languages again, and we're going to do a couple different things with lambdas in them. We'll look at the sort version first. So in this case, we're sorting by the length of the strings. So we have our integer compare there being turned into a lambda, essentially. So we'll look at the bytecode real quick. And what we'll see here is we don't actually have any call out to the compare operation there. What we've got is this invoke dynamic. And so the magic here of Lambda is that invoke dynamic lazily creates, essentially, an inner class at that point in the code. We don't have to have the class file. It generates it at runtime as needed. And then we can reuse that same object every time. We don't constantly recreate the inner class object like we did with the old pattern. So here's our Lambda body. It actually is inserted just as a static method into the class. So at runtime, the JVM can create our inner class, generate that code for us. It's much easier for us to distribute, and we don't have all the extra logic. So what about the JIT? This is the interesting bit. So the problem here, in order to inline code, we need a consistent target method. We need to call the same target method and class every time. And we need to see a single path through the code. So all the time we're calling the same piece of logic. It's not changing. We can optimize it. Now the problem is collection.sort is used by everybody in the system with many different lambdas. So we have lots of different lambda calls, lots of different lambda bodies that we see, and many different paths. And the JVM just can't optimize through this yet. This is an ongoing piece of work that the JVM folks are trying to improve. So if we look at an example where we've got a couple lambdas here, methods like map and collect and so on inline. Map inlines just fine. Collect inlines just fine. But once it gets down to actually calling our lambda, that doesn't inline. And the JVM just can't do this right now. So we can have a solution. We'll write this code by hand. Here's a version where we basically implement the map and the collect ourselves, still using a lambda for the substring logic. So here's our lambda. Here we actually do the map of all of those initial values. And then eventually our collect at the bottom is just a toString. Same logic, but not using the built-in methods. If we look at the JITted code here, we can see our getInitials manually method there. We can see our apply, so it calls the lambda. And we can see our substring down here at the bottom. All of this inlines together like we want it to. Because we've written this by hand, we've essentially specialized it for our code. So lambdas can inline, but most patterns will not on current JVMs. And that's important to know. So what have we learned here today? We ran through a lot of this stuff very quickly. Hopefully you'll be able to review this later or ask me any questions you like. So the JVM is an amazing platform, but it's not perfect. There are things it can't do. And every one of these features has a cost. Lambdas may not inline the way we want them to. String switches may generate more code than we expect. And you'll be a better developer if you remember that, and if, like Alice, you aren't afraid to go down the rabbit hole. All right, Jakuyu, thank you very much. Now, we started just a minute late, so maybe is there any time for one question, two questions? Yeah, okay, one or two questions. Anybody? You can also catch me after this too. Yes, right here. Oh, we hang out for the microphone for a second. Okay.
When we switch using enums, what does JIT do? Table, inline, or another?
So what does the enums basically compile down to?
Yes.
So enums specifically were designed so that they would be a contiguous range of values. So generally in the code it will actually be a table switch. And enums, even though they look like they might be kind of heavy, the JIT compiler, the JIT, will pick that up and should turn it into a fast table switch in every case.
Thanks.
Okay, and so yeah, come and grab me outside. And again, thanks very much.